Thank you for joining the Fire Suppression Systems Association webinar on Understanding Optical Flame Detectors. Your phone lines have been muted. If you have any questions during the presentation, please type them in the question box on the bottom right-hand side of your webinar control box, and we will take them throughout the presentation. This webinar is being recorded and will be available to download along with the slides after the presentation is over. With us today, we have our webinar committee members, Todd Stevens with Canistraro and Phil Gunning with Victaulic, and our presenter, Mike Hosh with Daktronics. I'll now turn the mic over to Todd to introduce our presenter.
Well, thank you, Becca. And again, welcome everyone to today's FSSA webinar on understanding optical flame detectors. Really excited that you're here with us today. And we're excited that we have Mike to present to us with this great topic. Before we get started, I do want to mention that we are moving forward. FSSA's annual forum is going to be held virtually at the end of next February 2021. So please mark your calendars. The specific dates will be coming out shortly, so you can watch for that through email and on our FSSA website. But I wanted to mention that our virtual annual forum next year is going to be unique and much more unique than any of the annual forums that you've been attending over the last year. We're really excited to present something that's specifically, it's more virtual, allowing you to create an avatar, allowing you to be more involved and get a chance to really interact with other members that will be at the annual forum. So we're really excited about getting more information out to you, so keep an eye out for that. With that said, I will introduce our speaker today. Again, it's Michael Hosh from Daktronics, who is a lead applications engineer. Michael has worked for Daktronics for over 30 years, almost entirely focused on utilizing optical flame detection to help customers protect lives and property. He has extensive experience in the application of flame detection and enjoys educating others about the benefits and limitations. Most recently, Mike is focused on solutions and providing application guidance for military aircraft hangars, as well as the manufacturing industry. I know this is going to be a great presentation. We appreciate everybody's attendance today. And with that said, Michael, I will hand the mic over to you.
Thanks, Todd. We'll get started here. I've got a presentation that should go through about 30 slides or so. And thank you all for taking time out of your busy schedules to join us today. I'm going to proceed here with our presentation, and throughout, if you need to ask a question or something, feel free to use the chat function and interrupt me, and I'll try to do my best to answer any questions along the way. So today, yeah, we've had some introductions already. My name is Mike Hosh. We're going to talk about optical flame detection, the what, why, and where of it. We'll go through some of the different popular technologies that are used for the detection of unwanted flames. And we'll look at some of the considerations that you can look at to try to optimize the performance of a flame detector. And then we'll have a short question and answer section at the back end. So what I find if I'm going to do a presentation, sometimes it helps me to break the ice a little bit and speak just a bit about myself. And I've been with our company, as Todd said, for over 30 years. I've worked there for 32 years now. And when I started, I was a technician on our production floor, and I worked doing that for a number of years, and kind of worked my way through a bunch of different positions in the company. And maybe about 14 years ago now or so, I moved into the applications engineering role and did a lot of traveling to customer sites around the world, and really learned the other side of it instead of just being a manufacturer, but where the products go and how they are used in the marketplace. And so I'm glad to spend some time with you today and try to explain these things that we call optical flame detectors to you. A little bit about the company I work for. I work for Detector Electronics Corporation. You might have heard of us called daktronics. That's our name. We're headquartered in Bloomington, Minnesota, just south of Minneapolis. And we operate a full systems center and our engineering test center as well. That's located just a few miles away from our corporate headquarters. We not only do flame detection, we also do combustible and toxic gas detection and the systems that the detectors tie into as well. So just a little bit about that. We are owned by Carrier. We were formerly part of United Technologies, but that transition just occurred this last April. So let's start about answering some questions. So what is a flame detector? Perhaps this is new technology to you. Perhaps you don't work with it very often. That's kind of what we find. It's kind of a specialized area. When we look inside of NFPA 72, the National Fire Alarm and Signaling Code, it's got a very firm definition there. It says a radiant energy sensing fire detector that detects the radiant energy that is emitted by a flame. And there's a lot of words there, and really what it amounts to is this is a device that detects a flame and provides an output to provide notification that that fire is existing. And when we're looking at it from our perspective, we're looking for unwanted fires. So unlike burner control or burner management control that can also utilize flame detectors, these detectors typically look for, I'll say, just an unwanted fire. So typically 99.9% of the time, they're just looking off at a given area and trying to look for a flame that might end up causing damage or harm. When we look at the question of why would you choose to use a flame detector? Well, there's a lot of different reasons. Some of it might be that it's actually a requirement. So when we look inside the different fire codes like NFPA 72 or NFPA 409 or all of the different NFPA codes, there's several of those codes that they're fairly prescriptive and they require you to use a flame detector in certain spots within a facility. There might be an insurance reason why. So oftentimes an insurance carrier may require that we have certain level of protection on machinery or processes in order to protect the facility or possibly people. Your authority having jurisdiction, your AHJ may require it. So you might have a state fire marshal or somebody who's in charge of a facility feel that this is a good reason to have it and putting it in to save people their lives. We look at, there's also risk-based engineering evaluations, recommendations that come in and require it. Any situation where you've got a very expensive process or maybe a shutdown that occurs, it's going to cost a lot of money and put people out of work for sometimes weeks at a time. You look at some of the refinery fires that have happened and how it affects not only the people that are at that facility, but the rippling effects throughout the entire economy. This is sometimes good use for flame detection. And other means of detection of fire may be too slow. So we'll look at some of those things as well. And sometimes people have just learned through experience that they prefer to have an optical flame detector present on a given process. I assembled this slide to try to give visually a picture of where we use flame detection. The upper left-hand corner is in an automotive spray paint booth, so that's a very popular spot when you get these robots that are painting a vehicle chassis or the vehicle itself. Fire can happen there, and you can imagine the amount of damage that occurs if that fire is allowed to keep burning. Aircraft hangars, another popular spot for them. We have lots of flame detection systems inside of aircraft hangars, military and commercial airline hangars across the world, looking for a spill of jet fuel fire. And it's really a supplementary system in that case, because you've got building control system already, the heat and smoke detection equipment up on the ceiling, but for the protection of the aircraft, those aircraft can be very expensive, as we all know. So protecting that asset can prove to be worthy of flame detection. Chemical storage rooms. We also have floating production storage offloading ships, compressor stations, truck loading racks, and turbine enclosures are some of the popular ones, aerosol fill as well. So those are just a smattering of examples of where one might choose to use an optical flame detector. A little bit on how they work, so the science behind them. If you look at the electromagnetic spectrum and the energy that is emitted and is around us at any given moment, there's in the middle, we've got the visible light. That's the area that our eyes can see. So when we look outside or we look at a fire, we could look at a given area, our eyes can only see a very, very small segment and range of that entire spectrum. When we look at a fire that's produced, well, different types of fires will emit different amounts of energy. And the goal is to select a flame detector that operates in a very, very tight, narrow bandwidth that is going to be able to detect a fire if it occurs. It's much like we have a large radio spectrum, for instance, and you have an FM radio, and you have lots of stations to choose from. But once I select a particular station on my dial, I can tune in and I can listen to that channel. But an FM radio receiver cannot receive or it can't receive AM signals or ham radio signals or things like that. So it's tuned specifically to detect FM radio. Much like that, as an analogy, if we have a UV detector, it's tuned to the UV wavelengths. It cannot see visible light, and it can't see light on the other side, which goes towards the infrared side of the scale. And likewise, if I have an infrared detector, it's tuned to specific wavelengths in the infrared area, but it's unable to detect the visible light or the ultraviolet light. So it can kind of work both ways. But the idea is to try to select an area that fire emits energy within and tune into that and only listen to that in an ideal world. That's a very difficult thing to do. When we look at the benefits that an optical flame detector offers, is the detector can detect fire from a distance. So unlike a smoke detector, that the actual byproducts of combustion have to come in contact with the measuring element, the detector is much like our eyes. So it can look out over an area, and if a fire exists in that area, it has a chance of notifying you that that's happening. So some spot like an aircraft hangar that offers a very, very large, big open space, a flame detector can pick up a fire, you know, a couple 100 feet away without any issue. Flame detectors are also very fast, relatively speaking. So there are models on the market that can detect fires in milliseconds of time, with as fast as 20 thousandths of a second, for instance. They, in terms, they're going to be able to detect fire in, say, 6 to 9 seconds. So compared to, say, a heat detector that might take 45 seconds to a minute to respond to a change in the temperature that's in a facility or in an area that it's monitoring, a flame detector, if everything is installed correctly, can typically detect a fire that's happening in just a few seconds. Detectors are able to check themselves frequently and make sure that they are able to respond to fire. There's also models that are available to be installed within hazardous locations. So this is a whole nother end of things when we get into it. I'm sure most people in this industry understand it, but if you don't, feel free to ask a question. But the hazardous locations are areas where there could be a level of combustible gas present at any given point, and which could become explosive. And the housing has to be of a certain construction to avoid igniting that atmosphere. So it's important as well. Also has to be resistant to environmental conditions. So the detectors can be placed outdoors where it is raining or snowing. It has to be able to take heat and cold and things like that, where generally your commercial solutions have to be indoors only. There are, with every benefit, there's also limitations, and some of the broader limitations of an optical flame detector is that they require some level of expertise. I can't just go to a local hardware store and purchase one and install it in 5 minutes and I'll be protecting an area. These usually take a lot of planning, they take engineering work, and this is a good reason why you folks are in attendance today, is to try to learn some more about it. It's never an easy matter to ensure the performance is going to be acceptable. Flame detectors are useless on a smoldering fire. So you might have something that's burning, such as coal, or any kind of a deep-seated fire that might smoke a lot, or maybe it just smolders, but there's not visible flame. That is a big limitation of optical flame detection, is that it can't detect that. We actually need flame present, or the emissions of the flame present. You have to have a good clear line of sight. So I put a picture there that I took many years ago of a detector that was installed at one point, but then somebody went and installed a different pipe in front of it, and really limited that detector's area that it was going to look for fire at. So unlike a smoke detector where I can put it up on the ceiling and the smoke will find its way to it, the detector has to have a view of the area that it's trying to monitor. And lastly, flame detection costs a lot more money than a commercial solution. Not only do the detectors cost money, but the installation costs a lot of money as well, sometimes as much as double what the price of the detector was. So it can be an expensive adventure to get into when you do these things. The goal for any optical flame detector is to detect fire anytime and anywhere it exists. The detectors also have to resist sources of false alarms, and we want to be able to send an alert to the customer when a detector is unable to perform or unable to detect a fire, or is having a problem for some reason. So these goals, these 3 points, might seem quite simple, but in reality, it's very difficult. Detecting any type of fire and anywhere it exists is a tall order, and we'll get into some of the reasons why that's difficult shortly. Resisting sources of false alarms. Well, false alarms sources are all around the detector constantly. It has to view these things on a continuous basis, and in an ideal world, it would always be able to discern the difference between a false alarm source and an actual fire. In reality, that's a very difficult, tall order to fill, but that is the goal. And we have to also be able to inform somebody if the detector, for whatever reason, is not going to be able to detect a fire. That's a very important point. When we look at the different detection factors, there's several things that contribute to whether or not a fire, a given fire, is going to be able to be detected. The first thing to discuss is the fuel type. So depending upon what the fire is comprised of, determines what level of radiant energy is emitted and also what frequency of light is emitted. And it's important then to select a particular sensor that is tuned to be able to detect that fuel type. It also makes a difference how far away the detector is from the given source of fire. Also depends upon how large the fire might be. So if we're talking about a fire from a cigarette lighter being your target fire, or we're talking a fire of, say, a jet fuel spill that's 10 feet by 10 feet or 100 square feet in size, the range on this might be completely different depending upon the detectors, and the settings, of course, figure into it as well, as there's different sensitivity settings within each detector. And also, what is the environment the detector is going to be placed in and what it might be faced with at the time it needs to detect fire. So if it's raining out, or if there's other environmental factors that could figure into it. So all of these things kind of play a part together to determine how well a given fire is going to be detected.
Mike, we have a question.
Yes.
The question is, what is solar blind? How is it related to the flame detector's performance?
That's a great question, and thanks for asking. Solar blind refers back to the ability of the detector to not respond to sunlight or the reflections of sunlight. So again, depending upon where the sensor's wavelengths exist and what the bandwidth is of the sensors, the goal is to be able to eliminate sunlight completely and not see sunlight. So that's where the term comes solar blind, means it's blind to solar energy. How it relates to this is, of course, if a detector is outdoors and it gets a view directly or indirectly of the sun or the reflections of it, how does that impact the detector's performance, being able to detect fire, or does it interfere with the detector's ability to detect fire, or might it go into a false alarm due to sunlight? Those are some of the things that you'd want to look at when evaluating a detector for use in your application. Now, if you're going to be completely indoors at that point and not around the sun, well, then solar blindness doesn't make much difference. But a lot of these detectors end up outdoors, and certainly understanding the effect that the sunshine has on them is important. Does that answer the question?
Yes, thank you.
I realize we're using the chat, so I guess it's kind of hard to answer that.
Yeah, that was good. I understand.
Okay. Okay. If not, just ask again and I'll try to explain it a different way. So when we look at the field of view of a detector, the field of view is really what the detector can see at any given moment in time. So much like our eyes, the detectors look out over a given area. But just like our eyes, and our eyes are seated in our skulls, and our skulls prevent us from seeing, say, behind us, for instance. It's not capable of doing that. Our eyes aren't, and neither is the flame detector. So the detector is limited by its physical construction of the sensor and also the mechanical housing and the placement of the sensor within that housing, how much of a field of view you might have. That's like the mechanical side of it. But then probably more importantly, or just as importantly, is the detector, its performance and its ability to detect a fire is going to be related to the characteristics of the fire itself. So again, going back to the fuel that the fire is comprised of, if I have a hydrogen fire, it's going to possibly emit much differently than a gasoline fire, for instance. Also the size of the fire, well, that size of that cone that I'm showing there will get proportionally larger depending upon the size of the fire. And really, these detectors can see things that are several hundred feet away or even larger or longer distances if the fire would be larger. Ideally, that field of view is going to be represented by a third-party performance listing. So companies like FM Approvals does approve different fuels and different size fires approve the detector's performance to those fires. So if you look inside of a given manufacturer's instruction manual, you'll see different fires listed and then whether or not they are approved. And when we go, yes, please.
Oh, I thought you were going on to the next slide. I apologize.
Oh,
do you want to keep going? I'll ask you when you.
Well, just the very last point I was going to make is on that drawing in the center there, which is your layout drawing. If you're trying to determine how many detectors to use, it's just a good rule of thumb that the optimal design will have no gaps in your coverage. That's also a NFPA 72 requirement that when you do go to design a system, you need to understand all of these factors and what a given range is going to be to that flame detector, both looking straight ahead and looking out of its peripheral vision or its off-axis performance, and then design the number of detectors and the placement of them to ensure that the areas are covered adequately. But yeah, you had a question now?
Yes, it's regarding IR detection. And after it's been in use for a while, what would cause the need for it to be calibrated again if the detector is showing a fault?
Well, there's several things that can contribute to that. If it's showing a fault, we're going to get into that in a few slides of some of the things that the detectors do. But if it's showing a fault on a high level, that's that going back to our slide of the goals. The detector's just simply informing you that its performance has been affected. Now, if it needs to be recalibrated, there's different definitions of calibration, but in our case, with a daktronics detector, we have a circuit that's called optical integrity. And optical integrity verifies the cleanliness of the lens and the sensitivity of the sensors once per minute automatically. If for some reason that source gets out of calibration, some things that could cause that would be if somebody replaces the reflector, the reflector element on it, swaps them between detectors, removes and replaces it, things like that can cause it. Typically, recalibration is not necessary. Sometimes, and most often, cleaning is necessary. So somebody's got to be able to go out and clean the detector's optical surfaces because it's just telling you that it's dirty and its performance has been compromised. So hopefully that answers the question.
It did. I failed to mention it was the OI calibration, the optical integrity. So you answered it. Yep.
Very good. All right, let's proceed to the next slide then. When I look at the field of view varying by the fuel size and the fuel and the size of the fire, I put together a few examples here that show the same detector on the same setting, but viewing different types of fires. So the one on the left is a methane fire and 32-inch plume of methane fire with our detector set at medium sensitivity. And this is a representation of the field of view. So it's as if you were looking down onto the floor with the detector being at the bottom. The detector can see 70 feet or 21 meters on axis down the center. Off axis, you can see at 15 degrees, it can see that same amount. At 30 degrees, it can see that same amount of distance. But at 45 degrees, it kind of cuts off the corners a little bit. And you're going to see a little bit of reduction in detection capability down to 50 feet or 15.2 meters at 45 degrees. Now, if we take that same detector and apply a heptane fire to it, you can see the range is substantially different. And the off axis is also a little bit different. When we look at methanol, for instance, well, the on axis range will be the same as well as the off axis range. So sometimes it can appear to be similar, but depending upon the fuel and also the size of the fire, these graphs or the resulting performance is going to be different.
Another question?
Yes.
This has to do with the speed of detection. Are you going to get into that, or should I ask it now?
You can ask it, sure.
All right. Does your high-speed detection system have the ability to detect and have water at the nozzle in 50 milliseconds or less on a deluge system for explosion purposes?
Yes, it does.
Explosion.
When you configure a UV detector or a UVIR detector or an infrared detector, the detector itself has that capability to respond to that sort of a fire from those sorts of compounds in a very, very short amount of time. As I mentioned before, the detector itself can respond, a UV detector, in about 20 milliseconds. An IR detector that our company manufactures will respond in about 30 milliseconds. But that's just the first step. So now that signal has to be given to a control system. And that control system has to be able to respond to the flame detector's input, and then in turn activate a solenoid to relieve pressure on a pilot actuated deluge valve, typically used for ultra high speed applications. And that valve and the solenoid acting together, we've got systems in place that will respond from front to back in around 40 milliseconds. So 50 milliseconds, much again depends upon the type of material that you're using, how far away the detector is from that material, and what energy that material emits when it does catch fire. So is it capable of doing it? Yes. Will it do it 100% of the time, all the time? No, but not without some work. So one needs to understand what the material is and the placement of the detector in relation to that material that's going to burn, and the amount of material, the amount of fire that's going to be there as well. So hopefully that helped to answer that question.
Very good.
All right, so when we look at the next slide on radiant energy and the inverse square law, the energy that a fire emits complies to the inverse square law. Other things like audio energy also complies to that. So if to use an example out of, say, real life first, if I was to be speaking at a given volume and you could hear my voice at that given volume at a given distance, if you were to double your distance, I would need to speak 4 times as loudly for your ears to hear me at the same level that you could when you were at the original distance. Energy that's emitted from a fire, the light energy, conforms to that same rule. So if I have a given distance, if I take and double that distance, I'm going to need basically 4 times the amount of the original energy. If I triple the distance, I'm going to need 9 times the amount of energy. And that just keeps going and going, and it never stops. So as your distance increases, the intensity decreases proportionally. But if I use a larger amount of fire, I can basically double my detection range as well. So just showing that that relationship exists between the amount of energy that a given source emits and the ability of a detector to detect it. When you look at configuring a flame detector, just your general rules is that your first thing is that it's very application dependent. So what sensitivity I select, for instance, the person who asked about the ultra high speed system, I'm going to use a different detector and a different setting on that particular application than I would in, say, a turbine enclosure or in a refinery or an oil and gas application. I'm going to use different settings to accomplish those things and give me the best possible balance between flame detection performance and false alarm resistance. Generally speaking, there certainly is a relationship between false alarm rejection and the sensitivity selection, meaning the higher the level of sensitivity that is selected, the greater the risk is of a false alarm. Now, much of that is also application dependent because sometimes you don't have given false alarm sources in a particular area, but sometimes you do, and that's where this balance comes in.
So Mike, we have another question that's in line with what you're talking about.
Sure.
It's what is the fire size and distance for the less than 50 microsecond detection for paint booth applications?
Okay, for a paint booth application now. So there again, we've got several FM listed fire sizes that equate to the amount of product flow, like lacquer thinner flowing through a nozzle and then catching fire. And certainly the size of fire that exists, probably the minimum to do that would be probably, say, a 3-foot fire from a robot. And so the fire size being about 3 feet, and the distance for that capability on some of the products that we have, it's probably going to be no more than about 15 feet away. So you need to be relatively close, I'll call it, to be able to achieve that speed of response. Now, as you increase distance, say I'm 30 feet, well, if I have 4 times the amount of fire, I could still detect that fire easily, say within the half-second NFPA 33 requirement. And you'll see a lot of that in your automotive spray painting booths. But to get the ultra high speed, generally speaking, the closer you can place the detector to the area that's needing to be monitored, the better. So it does not work at, probably more than, I'll say 20 feet away. You're not going to be able to get that speed of response unless the fire or the explosion is very big.
Okay, and one more question on the same line.
Sure.
Can the flame detector give a false alarm if it's being used to provide a signal to the releasing panel for an FM200 system?
Say that again. Can a detector?
Yeah, I read it differently. I'll read it as it's typed in. It says,
Okay.
Is it okay if we depend on flame detector to give a signal to pre-action panel for FM200 system? Can the flame give us a false alarm?
Well, the flame can give a false alarm, certainly, depending upon what it is that the detector is showing. So I'll give an example. So a flame detector is monitoring an area and somebody comes out and starts welding in that area for some reason. And there's some grease or oil on the material that's being welded, and that momentarily catches fire. Now, to that person who's doing the welding, they maybe would consider that to be normal, and just a result of them welding, that just happens. Sometimes little fires happen and they use a rag or their glove and tamp it out and there's not a problem. But if a flame detector is going to view that, it can't discern the difference necessarily between a hazardous fire or an unwanted fire that it's looking for versus that fire that just occurred when that person was welding. And if that does occur, that's when a discharge could happen. So not sure if that answered your question or not. That's an example of how it could happen. But yes, when it's hooked directly to a pre-action system, it's going to give the signal to be able to release. And the detector itself can't do that. That's got to be tied to a system that the system's then going to give the signal to do the deluge. So that you never use the detector itself to initiate that, but in effect, the detector is initiating it, but its output always has to be tied to a listed panel.
Okay. And
Okay.
I do have another question.
Okay, no, that's fine.
Regarding fuel type, the fuels listed in the FM approval guide is dictated by FM through their standard, the 3260 standard. We have diesel, but we don't have crude oil on the list.
That's correct. That's correct. We don't have crude oil on our list because crude oil is a natural product, and it's really impossible for us to obtain crude oil. Not impossible. We've got some, and we can show how a detector reacts to crude oil. What we find is that the actual gas content of your crude oil varies depending upon where on the planet Earth it's gathered from. And the exact response is always best determined through actual fire testing. So we do this quite frequently as a service for our customers. If either the customer should test that themselves, or we can do it in our test center if we're to receive a sample and have to get pre-approval through our EH&S department and so forth. But if we are able to obtain an actual sample of the crude oil of question, we can ignite that in our test center and develop test data for that particular application to that site. Now, the reason why we typically use diesel fuel as an alternative means is because through experience, we have learned that most closely diesel fuel represents crude oil fires. Diesel fuel is a heavy hydrocarbon that produces a lot of the really orange looking fire. If you look at one, there's also copious amounts of smoke, very similar to what crude oil does. In fact, diesel fuel generally may be a conservative fuel to select in place of crude oil when you don't have any other choice other than to try to test it yourself, because the diesel fuel does not contain a lot of the natural gases, the propanes and ethanes and methanes that your crude oil will in its true form. So that's why a lot of times if somebody asks us for an opinion on crude oil, we will reference diesel fuel data.
Thank you.
Okay. Thought we go through quickly some of the benefits and limitations of each one of the different types of technologies. So UV technology was really the first technology used for optical flame detection. It's what our company started with back in 1973. It's best suited for the fire types that are listed in the blue box on the left. So sulfur, paper, hydrogen, munitions, any place that's indoors, metal fires, magnesium, those sorts of things, and power grid arc detection. It detects nearly every type of fire that is present, that can happen. So we're talking hydrogen or hydrocarbon-based fires. We can put water or ice on the front of the detector and it doesn't inhibit its performance. It is capable of detecting arcs and sparks. It does not respond to radiant infrared energy that's emitted by processes, and UV flame detection is capable of ultra high speed detection. Now, with every set of benefits, there comes limitations as well, and I think these are just as important to let people know about. If you do get oil onto the optics of a UV flame detector, it's going to inhibit its performance. This technology is sensitive to other sources of common UV, such as lightning. So we put a detector outdoors, and if there's lightning, UV detection will pick that up and will go into an alarm just as if it was in a fire, detecting a fire. Some other common things: welding, arc, sparks, halogen lamps, and X-rays are all potential false alarm sources, so it's things to watch out for. We also have UV attenuating vapors. A real common one is ethanol, for instance. If you were to pop a hole in a drum of ethanol and spill it on the floor, the resulting vapor would absorb any UV energy that would be emitted by the fire. It might either delay or prevent its response to that fire. And a lot of times when they were used outdoors, we would use alarm time delays to ignore things like short bursts of lightning and things like that. But by doing that, that inhibits the detector's ability to detect short duration fires, like momentary fires, little flash fires. When we look at single frequency infrared, this is another technology that was developed in the early 80s to respond to some of those limitations that UV had. So single frequency infrared is capable of detecting hydrocarbon-based fires. You can put oil on the front of it and it really doesn't inhibit its performance in any way. It's just like it's transparent to it. The technology doesn't detect lightning, the arcs and sparks and other sources of UV energy anymore. It's unaffected by those UV attenuating vapors. It's less affected than UV by smoke that might occur between the fire and the detector itself. And it can detect partially obstructed fires better than UV technology. So if you have a fire that starts behind a process or piping, if the base of the fire happens to be obstructed, UV technology is going to struggle with that because that's where the chemical reaction is taking place. But IR technology sees really energy across the whole physical fire, so it isn't dependent just upon seeing fire at the base. We use these detectors typically inside of powder coating booths, printing applications like your big printing machines, paint spray booths, and aerosol fill applications. The limitations, as I mentioned, every benefit has some limitations. So if we have any sort of background that's producing a lot of infrared energy, a lot of heat energy, and that source is modulating or changing in frequency, that action can reduce the detection range of the detector, and it can become a source of false alarm to a single frequency infrared detector as well. If we get water and especially ice buildup on single frequency infrared detectors optics, it's going to reduce the detector's detection range, and it could even block it completely. And again, using that alarm time delay inhibits the detector's ability to detect some types of fires. So that's kind of common between all of these. In the mid 1980s, the idea was to combine both ultraviolet and infrared technologies into a single detector. So a UVIR detector offers all the benefits of the UV detector or the IR detector, but is combined in one unit. So you get all the benefits and you get all of the limitations of both UV and IR. We most typically use UVIR really anywhere indoors is a good application for it. Aerosol fill, munitions, paper machines, and really most hydrocarbon hazard applications. UVIR is probably the largest installed base of optical flame detection in the world, just simply because it's been around longer than anything else. It's been there since the mid 1980s. So when we look at its limitations, well, all the limitations that we had with UV or with IR still exist. So the oil on the optics, and the UV attenuating vapors affect the UV side. On the IR side, we got the random modulating IR backgrounds and ice on the optics. And of course, that alarm time delay inhibiting the performance again. Last one we'll speak about is Multispectrum IR. Multispectrum IR was introduced in the very late 90s and has been around basically for 20 years now. And out of all of the detectors that we manufactured, this is probably the one that is most popular because it serves probably the biggest range of different applications. We use them inside of automotive spray paint booths, aircraft hangars, engine tests, stands, your offshore platforms inside of refineries. They're good for hydrogen detection as well, floating roof storage tanks. The list kind of goes on and on. I just kind of put some of the most popular ones here that I thought were mostly important that people might recognize. The benefits of multispectrum IR is it's capable of detecting hydrocarbon and non-hydrocarbon based fires. So we actually have a couple different models that allow us to do that, but some companies will put that capability all in one detector, which comes with its own set of challenges as well. Compared to other technologies, multispectrum IR has a superior level of false alarm rejection capability. So we already mentioned it doesn't detect, because it's IR, lightning, arcs and sparks, halogen lamps, or other sources of IR. It's unaffected by those UV attenuating vapors. The oil on the optics doesn't really inhibit its performance. And it's less affected by smoke than UV technology. It can detect fire at greater distances than any of the other previous technologies. And it can detect those partially obstructed fires better than UV or UVIR technology as well. So that's some of its benefits. When we look at the limitations, we've got, again, intense and randomly modulating IR backgrounds might reduce the detector's range. And it might become a false alarm source as well. If we get optics that are covered with water and ice, that can reduce the detection range. And they're not applicable for applications that require your ultra high speed. So you wouldn't use multispectrum IR, generally speaking, in an application where you had to have detection and water flowing from the nozzle in 100 milliseconds or less. When we look at, I put this slide together because of the group that is attending this today. I think it's important to look at all of these aspects. When you perform an engineering evaluation for a customer, there's companies that you can hire that will do this and come out and actually look at a given spot and figure out what you're trying to protect and the best way to do it. And many of your companies do these same things, but you're going to want to determine answers to at least these questions, and we have a lot more that we could give you as well. But where's the best place to install them? How many do you need? What's the spectral emission of the fire that's going to burn, so that you can select the best technology for the detection of that fire? How fast does it need to respond? What might some sources of false alarms be? And make sure that you do a real thorough job in asking those questions, because the more work that you can do up front, the better the end result will be for that customer. When we look at the different certifications and approvals, this is also an important aspect when you go into a given area. And if you've been asked to look at the needs of the area and helping somebody determine what they need to install, make sure you ask about the different approvals that are going to be necessary. So there's your hazardous location approvals, your class 1 div 1, class 2 div 2, and on those things. Make sure that we have the right product specified that can be installed and operate successfully inside of such a place. And also, you may be concerned about the performance approvals, as was mentioned earlier with the FM3260 performance approval, to ensure that the product that is being selected to be put into a given area performs adequately and meets the customer's requirements. A couple other considerations. I put together a few slides here to look at. So the detector itself is just that. When you buy one from any manufacturer, you're going to have a detector. But you want to make sure that the mounting apparatus is of a sufficient quality so that once you put that detector in place and aim it where you need to aim it and tighten everything up, that it's not going to move. A lot of these applications that I mentioned earlier have a lot of vibration associated with them, and things can tend to fall and move out of alignment fairly easily, and you'll never know that without doing a an inspection on a regular basis, which you're required to do as well. We do offer a laser aimer that allows the installer to determine where the detector is pointing. This particular picture shows it pointing straight ahead. There's another spot for the laser that allows you to look at the cone of vision, so it puts it off axis at 45 degrees and at 30 degrees for the up angle to allow that installer to establish the detector's field of view. Having the ability to test the detector both automatically and then manually is also very important. Our products and some of the other ones on the market as well do this by using internal test sources. And it's very important that that detector be able to tell you if it's unable to detect a fire and ascertain its performance on a continuous basis, because if it doesn't check it frequently enough, or if it only checks one of the sensors instead of all of them, it might give you a false sense of security. Using a product that has heated optics, if you're in an environmental situation or in a facility where the detector is going to be outdoors and it's exposed to constant steam and cold weather, you can get a buildup of ice all over the process equipment that's out there. And using something that's got heated optics will keep that ice melted off of the detector's optics and the face of it where it matters. We also want to mention the field of view sight limiter. Sometimes it's necessary to be able to control the detector's field of view so that it doesn't view things like process flares. If you're going to look at that sort of a flare, it's going to be able to detect it possibly, even though it's maybe, you know, half a mile away at times. But that fire can be very big during a process upset, and having a way to control the detector's field of view just to the area of interest is very important. Air shields can be important in certain applications where you have paint spray, or maybe it's powder from a powder coating booth that's floating about, or even in a paper facility where we're manufacturing paper towels or toilet paper and things like that. You get a lot of paper floating through the air. It's like paper dust, I'll call it. It almost looks like it's snowing sometimes, but using an air shield provides a positive airflow away from the detector, and it will help reduce the need to clean it as often. We offer a flange mount assembly for putting the detector into the roof of a geodesic dome tank. It's not for zone 0 applications, but for zone 1 applications, you can do that. And the last couple pictures there are of our diagnostic hardware and software, which in our case is called a flame inspector. It allows you to connect up to the flame detector and check its status. You can download event logs that list the detector's history of what it's been doing. So it will show you if it's in fault or if it's been an alarm, and if so, it leaves a time date stamped log behind of how long that event lasted. The last slide I have is really, you can see us, Daktronics, as a technical resource. If you're interested in more information, go ahead and go to our website. We've also got some videos up on YouTube for both flame and gas detection. We're in LinkedIn, and we can always do a live video broadcast as well. We like to do those from our engineering test center, where if you've got a specific need or question that needs to be answered, we can get you in touch with our experts, and we can actually light fire on camera and answer questions and go through your specific needs if need be. So I think with that, that's kind of what I've got. And I want to say thank you again to everybody for allowing me to present, and thank you to the FSSA as well. I really appreciate the opportunity to present. And hopefully this has been helpful and for people. So if you have any questions, feel free to ask them.
Mike, we have 13 questions to go. We wanted you to get through your presentation for those who had to make, time constraints. But of the 13 questions, 5 are daktronics product specific. So we're probably going to have you answer those last or offline. I can email you those questions.
Okay.
But let's start with a non-product specific question. One is, can the same detector look for fire, of different fuels? Can one detector be used for different fuel types, or is it only one type of fuel?
No, that's a great question, and I probably should have tried to mention that earlier. But yeah, one particular detector type can typically detect any type of fire as long as that fire is emitting energy in the range that that detector is sensitive to. So for instance, if we have a detector that can detect a hydrocarbon-based fire, that detector will be able to detect, say, a gasoline fire or a diesel fuel fire or a jet fuel fire or a methane fire like natural gas or propane, butane, ethane, ethanol, anything that has a hydrocarbon bond to it will be able to be detected. And now, to what extent or the range and how well it performs depends upon those other factors that I mentioned earlier. So on the fire size and how far away the detector is from that particular fuel. But yes, it is not fuel specific. It's not like a toxic gas sensor that if you buy one that detects H2S, its job is to detect H2S and only H2S. It can't detect carbon monoxide, for instance. These detectors are not specific to a particular fuel type. So that's a great question.
Okay. How close can you mount the optical detector to the potential flame source without adversely affecting detection capability?
Well, that's very application dependent. Sometimes these detectors can be installed very close to what they need to monitor, but keeping in mind that the detector, its view is going to be stopped by anything that's solid. So if I mount it next to a machine and I put it just, say, 1 foot away from a machine, well, I can only see 1 foot then. I can see that small little circle that it's going to look at just 1 foot away. Generally speaking, you want to be back far enough to take in the particular application that it needs to see, but not so far as that you're out of reach to detect the fire of interest. So it's kind of a, if somebody wants to give me more details about that specific thing that you're trying to work with, I can certainly work with you and we can come to a better answer. It's kind of a vague answer, I realize right now.
Okay.
There's not necessarily a limitation, that the detector has to be able to see the fire. So if the fire is right up next to it, that's going to be all right. Ideally, especially with a multispectrum IR, all 3 sensors have to have a view of that fire. So if the fire is so small as that only one of the 3 sensors would see it, for example, that might not prove to be the best solution. You want to be back further away from it.
All right. I'm going to combine the next 2 questions together.
Okay.
Is it safe to say that detector sensitivity may have to be adjusted after installation? Is it often that it has to be adjusted after installation? And the other question was, is the sensitivity adjustable in flame detectors?
Yeah, I'll answer it. First off, yes, the sensitivity is adjustable on flame detectors. In our case, you use either that inspector software, and you can hook up the sensor module to it and select a different sensitivity level. Or in the case of an Eagle Quantum Premier safety system, it comes through a different piece of software, but our detectors are fully selectable for their sensitivity, and that's not a problem. How often does it happen out in the field? That's kind of another application dependent question, but I would say not very often that we need to. We really would like to up front have our sales group work with the particular application well enough and know the people well enough that we get the right product in there with the right settings on it, so that right out of the box it could be set up and utilized without a problem. But it does happen, especially I'll give an example of an offshore platform when there's maybe 300 detectors that are installed on one offshore platform. When they're sold, say at a medium level of sensitivity. And so all of them go out as medium sensitivity. But then once they're installed, occasionally, I'll say maybe 3 to 5% may experience an issue, either in that the application they're going to be installed in requires greater level of sensitivity, or it might be the other way where the detector is installed fairly close to whatever it's monitoring, and whoever is installing it has the responsibility and the ability to speak up to their management and have a conversation and get the safety case examined. And they might choose to decrease that sensitivity from medium to low in order to gain false alarm resistance. How often does it happen? I would guess 3 to 5% of the time.
Okay. And then regarding testing of the flame detectors, will using a magnet or doing it manually confirm that it will work in an actual fire event?
What the test does is confirms that at that moment, the detector is able to detect a fire. And using the magnet, what that does is activates, at least in our case, what it does is activates the test routine manually instead of automatically. So you hold a magnet up to the product for 7 seconds, causes an internal calibrated source lamps to come on, and those source lamp or lamps comes on, emits a signal, goes out through the detector's optics, bounces off a reflector, comes back in through the optics and into the sensor and creates a signal. If the detector's got 50% or more of its original detection range remaining, the detector will actually go into an alarm, and that allows you to test your entire control system that it's hooked to. So if you were to do that, you'd want to inhibit your suppression system or the executive action that the system's going to take so that you don't inadvertently get wet when you're doing the test or cause a full-blown alarm situation. That's what that does. Did I answer all that question or not? I'm sorry.
No one's coming back with a follow-up, so.
Yeah, I think,
okay.
So yes, it does test it. Does that guarantee that it's going to detect a fire? No, it does not. A fire is just that, it's unpredictable. We don't know the type of fire that's going to be predicted or that's going to occur. So the best that can be said about that, or that I can comment on, is it's not a guarantee, because once you test it, you know that it's good that minute when you walk away. Now the automatic test that happens every minute takes over, and that will confirm that the detector is able to detect fire once a minute. After that, if the detector becomes blocked by ice, let's say, or a bird dropping on it for some reason, and it completely covers the detector's optics, after 3 failed tests that are consecutive, so after 3 minutes of testing, the detector will indicate a fault condition, in our case, telling you that that detector needs service. And if you were to ignore that for some reason, that detector might not be able to detect a fire should one occur, if it's completely blocked, for instance. And also, as I said, fire is unpredictable. So the goal is always to try to detect fire, but there are no guarantees. We can't guarantee that that's going to happen, but it certainly, that is the objective, is to try. As I said at the onset of the presentation, the goal is always to try to detect fire.
Okay, as a follow-up to that, one question is, what is the preferred method to keep water and ice off the lenses? Heater or pneumatic air curtain? That was the question.
Yeah, so water itself, if it's raindrops, usually aiming the detector downwards, which is how our instructions are going to instruct you to do it, Gravity itself will pull the water off the detector, so it's not just a droplet that's sitting on top of the lens. So that's number one, is to aim the detectors downwards so gravity helps you. The next thing is we do offer a weather shield, and alongside that field of view sight limiter that I showed in the presentation. If I go back here a couple slides, this weather shield that's in the middle provides kind of like a rain gutter around the detector, and as the detector is aimed downwards again, you know, water doesn't typically flow uphill, so wind can blow water droplets onto it. But by using this weather shield and aiming it downwards, that prevents a lot of it from happening. The other thing is we have a built-in heater on these detectors that will help to evaporate the water that does accumulate on the optics and keep it operational for a longer period of time. But yeah, usually air shields aren't real practical. If it's in an outdoor application, that's not what they're really intended for. So it's usually more of a physical barrier like that weather shield there that I'm showing.
Okay. And Mike, if you answered this, I apologize. I was going through the questions, but how are the detectors tested or proved out in the field after installation?
Yes, sure. I did not touch on that. So out in the field, they need to be tested with that magnet, as I'm showing there. So at least yearly, you have to go to the detector and test it. And that's a manual optical integrity test. So when you hold that magnet on the lower right side there up to the detector, it causes that test routine to execute. And when successful, it will go into alarm, and that will allow you to test the control system that it's connected to as well. And that is the manufacturer's prescribed method of testing our detectors, and is also recognized by FM approvals as a suitable way to test it. The other way, if the detector is mounted at height or in an inaccessible area and you can't get that magnet to it, you can choose to run a fuel wire out of the rear housing from a terminal called manual OI down to ground level, maybe to a key switch or to some other sort of a switch, where you can connect that wire to a DC minus, and that will cause the test routine to execute as well. There's also an extension pole that gets you, I think it's like 17 feet. You can put the magnet on the end of that and reach up to get the detectors that are, you know, a story or so above you. So once per year, you need to go out and at least once per year check it in this manner. And that's all really you need to do. If it's clean and it's operating, it'll tell you if it's not. There's a green LED on the front of these products that will turn yellow if it's in a fault, and also fall relay de-energizes, and the system that it's connected to is going to receive a fault. But for testing it, that's all you really have to do.
Okay. Moving on, does munitions include machining operations for HE?
Machining operations for HE, meaning?
I don't know if it's highly explosive. I'm not sure what.
Explosive, but yeah, machining operations, when we say munitions, we're really talking about, you know, that's just a broad category. But yes, if they're demilling old munitions compounds or destroying it, getting rid of it, these products, I've seen them used successfully there. But certainly milling operations where maybe they're forming a pattern in a piece of energetic material so that it burns properly when ignited. Yes, I've seen detectors put in those spots as well. So yes.
Okay. Could you explain flame flicker detection?
Yes, I didn't put that in this presentation just in the interest of time, but alongside the necessity for a detector to have energy that's of a specific wavelength, that's kind of the first gate, if you will, that energy has to get through before being analyzed further. So you see this picture here of the of our X3301 on the mounting swivel, and you see the 3 windows, and it kind of looks like a green piece of glass. So that's your optical bandpass filter, and any energy that's on the outside has to be able to get through that piece of glass to begin with. But once it's inside and it gets through that glass, so assuming it's of the proper wavelength, that energy then hits pyroelectric sensors that are sitting behind those pieces of glass. And that is like a crystal that's sensitive to light. And a steady state of energy, like from a lamp or just a heat source, is just that. It just is a steady state, and the sensor just receives a steady state of energy. And so the crystal does not bend or move and doesn't create any further signal. So that's why it doesn't work very well on a smoldering fire. But if a fire that we're trying to detect typically moves about, it changes in frequency, it changes in its energy emissions, it changes in the amount of magnitude of light energy that the fire is emitting. Now, as that fire light gets through that first bandpass filter, it then strikes the elements of the pyroelectric sensors, which create small electrical signals that are directly proportional to the fire itself. And then we know that a fire flickers anywhere between 2 and about 15 hertz. If we get something that's changing more frequently than 15 times a second, there's a filter inside the detector, the signal analysis or signal processing, that typically will cut it off and throw that signal out and say that is not a fire. So a fire has to show some level of flickering in order for it to be detected by these detectors. So a steady state fire, like if you just light a cigarette lighter and leave it burn, it's real smooth, it doesn't flicker very much, that fire isn't readily detectable by a detector that's looking for flicker analysis. But most companies employ some sort of flicker analysis in their processing, and that's done so that the detector can help further define and distinguish fire from non-fire sources. Otherwise, there'd be many lights and sources of a false alarm that would very easily trigger one of these detectors. So that flicker analysis helps to weed out and alarms from, or fire from non-fire sources.
Very good. All right, when someone orders an IR3 flame detector, which sensitivity is recommended and why is it important?
Okay, that's a real good question. So when they order it, we're going to start asking the person who's ordering it a lot of questions. What sort of application is it going to go into? What fire does it need to detect? How far away might that detector be from the area that it's trying to monitor? In other words, if you tell me the detector is for use in an aircraft hangar, or you tell me it's for use inside of a turbine enclosure, I'm going to probably recommend the same detector, but I will have different sensitivity settings that we can send and configure the detector for before sending it to you, so that when you open the box, it's ready to go. Now, why does it matter? Well, it matters a great deal, because if I put very high sensitivity, the very most responsive to fire configuration in every detector we sold, that would work fine in that aircraft hangar scenario. But if I put it inside of a turbine enclosure where maybe the engine is maybe only 7 feet away from the detector, that becomes a risk of false alarm at that point. And so we'd want to make sure as much as possible up front that we have the details of the application known to the salesperson who's selling it, so that we can try to select the best detector for you. So a lot of it is application dependent, and there's usually a lot of questions that go along with it.
Okay. Now, this is an applications question regarding outdoor transformers. Is it okay to use flame detection instead of linear heat?
Yeah, well, it depends upon, again, what you're trying to do. The flame detector is going to detect fire, especially for transformers. So if you're looking for a mineral oil fire that's going to come from the transformer itself, you know, leaking or having a problem exploding, yes, the X3301 Multispectrum IR works quite well for detecting mineral oil fires. We're looking at more like the arc detection, like if something fails in that transformer and there's a lot of electrical arcing, UV detection can be beneficial. Although we are not approved for the detection of arcs, UV technology certainly detects it, just like we talked earlier about it detecting lightning. Now, linear heat detection, that's a bunch of cable that is laid out over a given area, and it's going to respond to the change in heat. So once a fire starts and the byproducts of combustion start increasing the temperature around that cable will change states and the two wires either open or become connected depending upon the design of it. The big disadvantage of that is the time. So unless the cable is right in the fire, if it's above it, especially if it's outdoors, what about the wind and things like that that could maybe take the heat from the fire away if it's blowing very strongly, 30, 40 mile an hour wind. If the heat that's being emitted from the fire isn't hot enough to trip that cable, it might delay its response. Also, after a fire occurs, you have to go out and replace that linear heat cable, which can be an expensive adventure as well. But, you know, every technology has its space. But for detecting transformer fires, yes, optical flame detection is a possibility.
Okay. Another applications question regarding which type of detector to use, whether a hydrogen version or a regular multi-IR version for, is it nickel cadmium battery applications?
Yeah, NiCad batteries, that's a good one. That's even your lithium ion batteries, things like that. What we find is that, you know, these batteries, and there's a lot that's growing in this industry right now, and a lot of unanswered questions, frankly. But we do know that the gases that are produced when a battery starts failing typically do include hydrogen, but they'll also include hydrocarbons. And also, once a battery starts on fire, you've got the plastic typically that the battery is housed in, and of course the wiring and the insulation on the wiring, the polyethylene jackets and things like that that are going to start to burn and create kind of a plastic fire. And for that, we would recommend a hydrocarbon-based flame detector rather than the purely hydrogen-based one. So we would recommend our X3301 for that application rather than just the hydrogen itself. If we could always just guarantee that it was just hydrogen being present during that nickel cadmium battery fire, I think hydrogen would be good. But typically a fire like that starts is going to include a lot of hydrocarbon materials.
Okay. Another application, what kind of detector would you recommend for smoldering fires? Coal, for example.
Yeah, so again, optical flame detection does not work very well for that. In fact, it doesn't work. We would not recommend using one of our detectors, at least for that application. Now, what detectors to use? I think there's probably some, and we don't sell them. I don't have firsthand knowledge of these, but some infrared-based cameras that look, say, at the coal pile and can discern a hot spot. A lot of the issues with a coal fire is that the fire happens inside the pile of coal, and they might only see it visually with looking out at somebody operating a loader on the site and see a bit of smoke coming out of the coal, and then they literally have to dig out the pile and squirt it down with water. So possibly some sort of an infrared camera might allow you to view the coal pile and look into it. But short of that, if it's never ever supposed to be there, if it's on a conveyor or something like that, and it's going to be conveyored past, probably some sort of a camera that's based in the infrared with some good software may be able to help. But it's not something I'm familiar with, so I prefer not to really give too much direction or hope to somebody on that because I don't have the knowledge.
Okay. Is the SFIR detection based on a single IR detector, such as a PBS with a bandpass filter?
It is based upon a single pyroelectric sensor, just like the Multispectrum IR has 3 of those sensors in it. The single frequency IR has just 1 pyroelectric sensor in it that is sensitive typically to wavelengths of hydrocarbon emission being 4 to 5 microns.
Okay. A couple more questions here. Application question: gas turbine H2 fuel gas mixture. What type of detection would you recommend?
Yeah, so if you have a fuel mixture, and this is a question we're getting more frequently now too with syngas and things like that, our hydrogen-based model is actually FM approved for the detection of syngas, which is a combination of hydrogen and carbon monoxide and some other things as well, some methane in it. The general rule is you should always be putting in a flame detector that's sensitive to the emissions that the fire is going to present. The problem is with these mixed fuels is one cannot guarantee what the mixture is going to be on any given day. So if the mixture is basically at least 20% hydrocarbons, the hydrocarbon detector can be used. But I would say if it's more typically that you're going to have more hydrogen involved, that you would use a detector that's specifically suited for the detection of hydrogen. So we do have some information on that. I can take that question offline too and try to help whoever it is that's asking about which one to select. But yeah, generally speaking, the X3301 will detect your hydrocarbon-based fires. The 3302 detects your hydrogen-based fires. And if there's a mixture of that, if it's like a 50-50, either detector will work satisfactory. But yeah, we can work with you more on that as well.
Okay. What's your opinion on video-based flame detectors?
Well, my opinion is it certainly is it's another technology. And although this presentation, I focused basically on the products that I'm familiar with and I've worked with over my tenure at our company, I think it can be successfully used. Just like anything, it has benefits and it has limitations. And one needs to make certain that the approvals are in accordance with the customer's requirements. And again, I'm not here to talk badly about another company's products, and I do have some opinions on it, but I'll reserve those for myself.
All right, Mike. Well, all the other questions are more product specific, and how would you like to handle those?
Well, it probably would be best just because it's 12:30. I'm sure people are, or it's 11:30 where you are, 12:30 where I am, but people are maybe trying to get on with their days. It might be best if we were to compile those into an email and I can return the emails independently to people who are asking. Or I'm fine staying on too. I can stay and answer the questions if people want to listen. That's fine. I'm not in a hurry myself. I can spend as much time as is necessary, but however you think you folks want to handle it.
Todd, I'm going to refer to you and Becca for how you want to proceed.
Sure. Yeah, no, thank you, Phil and Mike. I think we're going to wrap it up. We do, this is awesome. Obviously, there's a lot of great questions. There's a lot of interest in the topic, and we appreciate everybody's involvement in this process and bringing the questions to light. But again, I know Mike put his email address up there, I think, earlier, and any additional questions, you could always send them to FSSA and we can get them to Mike. But I think what we'll do is we'll answer some of those other questions offline, Mike, via email and so forth. So again, big thank you to you, Mike. Great topic, great conversation. And this is the longest we've gone and probably the most questions we've had. So again, thank you to Mike. Thank you to Phil for helping ask some of those questions, and thank you all to the listeners as well. Becca, you want to wrap it up for us?
Yes, I sure do. So I will echo Todd. Thank you to Mike and Phil for joining us today, and for all the attendees. A few of you did ask about the presentation. As I stated in the beginning, the presentation will be available to download, and it was also recorded. So the recording will be uploaded to FSSA's YouTube channel. So thank you again for joining us this week on FSSA's webinar for Understanding Optical Flame Detectors. We look forward to having you join us on the next FSSA webinar.
Thank you.
Thank you, Mike.
Thanks, guys.